Hello, section 2.7 is going to talk about composing functions. So you did do quite a bit of this in Algebra 2 last year. So note I have review up here for you. And so we're going to start with composition of functions, and the definition is right here. The composition of a function is really just plugging one function into another. Okay, so it's pretty straightforward. So I have some functions up here, f of x, g of x, and h of x, and this is a square root function. And we're going to use notation like this, and if you recall, that notation means f of g of x, but we can also write it like this, and I'm not sure if we used that notation last year in Algebra 2. But you can do f with this little circle, which implies you're going to do f of g, or you can simply just say notation like this without the x. So again, all three of those mean f of g of x. So we're going to do these two examples right here, and if you want to, pause the video and try to do it, see what you can recall. Otherwise, I will walk you through that. So when you do f of g of x, you always start with the innermost, and so you're going to take the g function and then you're going to substitute that in for the f function. So note I took the g function here, and that's x minus 1, and then I substitute that into the x of f. So I'm really going to have x minus 1 quantity squared. So I wrote it like that here. You can certainly FOIL that out. I'm sure you're all okay with that. That's optional, up to you. Okay, now if I do g of f, okay, so going back to this one here, g of f, now I'm going to start with f of x, and I'm going to plug that into g. So starting with f of x, I'm going to plug that into the x of g. So instead of x minus 1, I'm going to have x squared minus 1, and that's it. So it's really just a substitution game. So that's what a composition of functions is. So again, I would pause the video and try these three here. So again, this one's saying do f of f. So you're going to put f into itself. This one you're doing three of them, so start with the innermost. So you're going to put h into g first, and then whatever that outcome is, you put into f. And then here you're going to do actually evaluate a number, so g of 4 first, and then whatever that outcome is, you put into f. Again, otherwise I will walk through these. So f of x means you take the function of f and you put it into itself. So you're going to put x squared into the x of x squared. So you plug in x squared and then you're squaring it. And of course, when you have a power on a power, you multiply. So you get x to the 4th. Now f of g of h means you start with h first. So that's the square root function up here. And you're going to substitute that into g. And the g is x minus 1. So I said, all right, I'm going to have x minus 1, but I replace that x with the h function. So I have the square root of x minus 1. Okay, so this is g of h. Then I take this outcome and I put it into f. So f says take x and square it. So you're going to put this now into the f function. So x squared, I'm going to replace that with square root of x minus 1 squared. And then remind yourself that that means FOIL. So you're really taking the square root of x minus 1 times the square root of x minus 1. And you should be comfortable with FOILing, but just in case. So you FOIL that out and you get an x. You get a minus 1 root x, another minus 1 root x, which is minus 2 root x, and then plus 1. Then lastly, you're doing g of 4, f of g of 4. So you start with g of 4. So I'll go back up here. G is x minus 1. So I'm going to substitute the x with a 4. So that's easy. 4 minus 1 is 3. Then you take that outcome and substitute it into the f function. And if you recall, the f function is x squared. So I'm going to take 3 and square it, and I get 9. And so 9 is your final answer. Like f of g of 4 is that. Graphically speaking, you can do these also. So I will walk through how to do this. But if you're doing this one right here, so you're doing f of negative 4, you start there. So remember, this is really an x value. So that means when x is negative 4, f of that will be your y value. So if you go up to x equals negative 4, that's right here. And then you're evaluating the f function, so that's the red function. So I would go down until I hit my output, and that y coordinate is negative 2. So again, I go to the x value of negative 4, go down until I hit my f function, and its output, which is the y coordinate, is 2. Okay, so this expression equals 2. So, negative 2, excuse me. So f of negative 4 equals negative 2. Well, then I take that output, negative 2, and I plug it into the g function. So f of negative 4 equals negative 2. Type that out. Okay, so that's what I did first. Then I'm going to take the negative 2 output here and plug that into g. So I go to x equals negative 2 right here, and then I'm going to the g function, so that's the blue, and its output is a positive 2. So this final answer is positive 2. Okay, so very quickly, I'll do this one. I'll use a different color. Let's do purple. No, we'll do green. So g of 4 means go to x equals 4, right? So I go over to 4, and I'm going to the g function, which is the blue. So that brings me here, and that output is a positive 1. So then I go back and I'm doing g again. So I left off at 1. So then I go to the x value of 1. And then I go back to g, and the g function is blue. And its output is negative 2. So this equals a negative 2. All right, that was section 2.7. So 2.8 is one-to-one functions and their inverses. And you did do all of this. I don't know that we used the language of one-to-one. So, but we definitely talked about inverses. So I would probably jot this down here. So a simple way to think of a function and its inverse is that the domain x and the range y have been exchanged. Okay, so you literally switch x and y, which you probably recall. However, not all inverses are functions. Okay, so here's maybe the new definition here. It says those functions whose inverses are also functions are called one-to-one. That's probably pretty important to write down. So if you have a function and its inverse is also a function, we call that function a one-to-one function. I just said function a lot. So, for example, if you look at this graph, you got a nice parabola, right? What does the inverse look like? Well, you're going to switch x and y. So if I take the point 0, 0 and switch it, that's still 0, 0. If I take the point 1, 1 and switch it, that's also still 1, 1. If I take this point, that's 2, 4. If I switch 2, 4, that's going to be 4, 2. So I'm going to go 4, 2 and put a dot here. And I'm going to put a dot here because those did not switch. If I go the other way, negative 1, 1, the opposite of that is 1, negative 1. So if I go 1, negative 1, that would be here. This point here is negative 2, 4. So negative 2, 4 flipped would be 4, negative 2, and you can probably already see that inverse function here. Whoops. So I will connect those points. I'll go to the next slide there. So that's what that inverse would look like. And is this inverse, is this blue graph a function? You can probably look at that and tell, no, it is not. And if you don't recall what makes something a function, quick do a vertical line test, right? So that vertical line goes through 2 output values. So this one x value has 2 outputs, making it not a function. So the original parabola was a function. Its inverse is not a function. Hence, this parabola is not one-to-one. So there's kind of a quick visual of that definition. So if you have a graph, so let's say this blue function over here is my graph, you can decide if it's going to be one-to-one if it passes the horizontal line test. So you don't really have to graph its inverse to find out. So if this blue is the function, if I do a horizontal line test with this pink line, I'm going through 2 points. Okay, that tells me that its inverse is not going to be a function. Hence, this function is not one-to-one. Okay, now that's recapped right over here if you want to jot that down. So a function is one-to-one if and only if a horizontal line does not intersect the graph more than one time. If you want to check both, you certainly can. So if you wanted to actually graph the inverse of this blue and then check vertical line test, you can, but this might save you some time just using that horizontal line test. So I'm going to give you a second to look at this graph, and we want to sketch the graph and determine if it's one-to-one. Okay, notice here, put it in your calculator. We're not going to dwell on graphing this by hand for sure. So I'll give you a second to, if you want, to grab your graphing calculator, type this into your y equals. A nice standard window will suffice, and you should see something like this. So feel free to pause the window or pause the video and take a moment to graph that. So rather than graphing its inverse, I can just do a horizontal line test. So if you see this horizontal line, it goes through 2 points. That tells me that the inverse of f of x is not going to be a function. So is this original quartic function one-to-one? It is not, because a horizontal line test goes through 2 points saying the inverse is not a function. Okay, one more. Again, if you want to take a second and pause the video, I would put this into your calculator. Be careful when you do this that you put parentheses around the numerator and parentheses around the denominator before you divide. And again, pause, take a moment, make sure you can see this graph here. Nice standard window again. This one is one-to-one because if I do a horizontal line test, and I showed several horizontal lines here, but I'm going through just 1 point. This horizontal line going through 1 point, going through 1 point, that's good. That means that both the original graph and its inverse are functions, meaning this is a one-to-one function. When you have the inverse graph, if you recall from Algebra 2, first of all, notation is probably important too if you want to highlight this here. But notation for inverse is f to the negative 1. Please remember that that is not like a exponent. So it's just notation, and that means you have graphed its inverse. So down here, the blue is the original function, and the pink is the inverse. Note that notation. Okay, the other thing to note is any graph and its inverse reflects over the line y equals x. Okay, so you can see that line y equals x. If I take any point here and reflect it over, I would come across there. So take this point, reflect it over, you would end up here. So if you're a very visual person, that might be easy to see. No worries if you can't necessarily do that, because you can always switch x and y coordinates. So if you'd rather do this right? You can graph the original function, pick any points you want, and then you just literally flip them. So if the point was 1, 2, your inverse point would be 2, 1. So you don't have to necessarily reflect around that line, but it helps if you're visual with that. All right, so we're going to find the inverse of functions. Then we're going to graph it, and you can use your calculator for that. And then you're just going to verify that it reflects over the line y equals x. And I also tossed in some domain and range here. So why don't you pause the video, take a second, and let's graph the square root of x plus 3 first. So I will give you a moment to do that. Okay, you can see the original function, the square root of x plus 3. If you type it in your calculator, it's kind of difficult to see where this point is. So maybe remind yourself the original, like just a square root function, the parent function. If you were to graph that, it starts at 0, 0 because you can square root 0 and get an output of 0, but anything negative would be imaginary. So that kind of looks like this. And then if you recall your shifting knowledge, this is going to take you to the left 3 units. So from 0, 0, I'm going to go to the left 1, 2, 3 units. In fact, all of these points will shift to the left 3, if that makes sense. Or use your table feature on your calculator to get those exact points. And then you can see, again, in interval notation that the domain is everything from -3 to infinity. So bracket -3, parenthesis infinity. The range is everything from 0 to infinity, because this is slowly rising. So bracket 0, infinity, parentheses. Okay, if you inverse the square root function, and my inverse is in blue here, note that notation, right? F to the -1. All of these points I just flipped. So -3, 0 is flipped, would be 0, -3. This point here is 1, 2. Flip that, and you would get 2, 1, etc., etc. And you can probably see that these are reflecting over the line y equals x, so that's kind of cool. Another really cool thing is because you flip x and y, the domain and range also will literally flip from a function to its inverse. So the range becomes the domain on the inverse, and the domain becomes the range on the inverse. Okay, so very quickly when you analyze a function and inverses, assuming the function is 1 to 1, if I say f of 2 equals 5, I'm really saying when x is 2, y is 5, right? So that's like just a coordinate point. So it would be like 2, comma 5 is what f of 2 equals 5 is saying. So if I said, what is f of -1 of 5? Well, if I know this is the original point on the function, if I inverse these points, then I know 5, 2 is going to be a point on the inverse. So then f of 5 would have to equal 2. A little more thought-provoking, if you have a function equals 3x minus 1, and I know that its inverse is 8, well, again, I know when I plug in x, I'm going to get 3x minus 1. So if I write that out as a function, right, this would be like my coordinate point. Okay, so then if I inverse that, I'm going to literally switch these. So now I'm saying when I inverse that, well, actually I won't type this out. So when I plug in 8, that's going to really be going in for my range on the inverse function. So I can say, okay, when does this equal 8, and solve that backwards, right? So when is my function equal to 8? And then, of course, you can do the math from there. So 3x minus 1 equals 8. So you'll add 1 and get 3x equals 9, and then divide by 3, and you know that that's going to equal 3. Okay, so function notation, inverse notation, they literally switch from 2, 5 to 5, 2, or from x and the f of x to the f of x and the x. Okay, last two concepts. If you have two functions that are inverses of each other, their compositions, we talked about that at the start of the video, should always equal x. So that means when you substitute the function into the inverse, you should get x. And when you substitute the inverse into the function, you again should get x. And that's all about that reflection. Remember how they reflect over the line y equals x? That's why when you composition them, you also get x. So you again did this in Algebra 2, but I'm going to remind you how you show two functions are inverses of each other. So if this is f of x and this is g of x, or again, this would be, if you want proper notation, this is the inverse of x. So I'm just calling g of x the inverse of f, if that makes sense. So I'm going to substitute this into the f function, and I'm going to substitute this into the g function, and that my outcomes should both be x for that. If you want to pause and try, otherwise I'm going to show you that work. Okay, so here we go. Here I took f of g of x. So I took x cubed minus 3 and substituted it in for that x. So x cubed minus 3 and then plus 3. Of course, those 3's cancel out. So I'm left with the cube root of x cubed. And that simplifies to x. And then the opposite, I would do g of f of x. So now I'm taking the f function, that whole cube root, substituting it in for that x. So I have that cube root and then cubed, and then minus 3. So the cube and cube root cancel out, and then the 3's cancel out, and you get x. So if you're asked to verify or show that two functions are inverses, that's what that means. You need to show that their two compositions equal x. All right, last example then is actually finding the inverse of a function. Again, you did in Algebra 2, but remind yourself that you are going to flip x and y, so you exchange them, and then you resolve for y, and you will have the inverse. Okay, so if you want to give this one a shot here, first you switch x and y, so this will become x, and these will both become y's. Okay, if you want to pause and try that, otherwise again I'll show you the work. So I switched x and y, so this is becoming x, and those are becoming y's, and then I want to resolve for y, and I have two of them. So I multiply the y plus 6 over, so I did that here, x times y plus 6, and then I distribute the x through from here to here. Okay, and then I get all my y's on one side, so I subtracted the y over here, and then I subtracted the 6x over here. And then I factored out a y because I want to get y by itself to solve for it. So factor out a y and you're left with x minus 1. And then you can divide that x minus 1 over, and you are left with the inverse. So there's everything you need to know about inverse functions, one-to-one functions, compositions. So good luck.